Hey everyone. Today we're going to continue our study of linear regression from both a theoretical and practical perspective. To do so, we're going to do a bit of coding. We're going to go through an example and calculate some p-values. Hopefully you'll find this helpful in understanding p-values and linear regression a bit better. I will mention, I made another video on linear regression, and you can find that linked below. This video builds upon it a little bit, but it's also somewhat independent, so feel free to skip it. With that in mind, let's get started. So the first thing I'm going to do is import some packages. So I'll always import NumPy, which is the Python linear algebra package. And I'll also import Seaborn. Seaborn's a plotting package in Python that builds upon matplotlib, but I like it a little bit better. And I'll need to put it in dark mode because that's what my IDE VS Code is in. And we'll go ahead and run that one. So I'm just going to create a bunch of random points. So I'm going to use NumPy to create a bunch of random points. Normal's not quite right. I'm going to use random. And I'm not going to use normal. I'm going to use uniform. So basically I'm going to generate a bunch of points between 0 and 1 at random. And I'm going to make about 1,000 of them, or exactly 1,000. So X will play the role of the independent variable. We're going to have 1,000 data points, and each one will be a single number. Now we'll create a target variable Y. And this is going to be 3 plus 2x plus some random noise, which GitHub Copilot correctly guesses what I want. The random noise will have mean 0, standard deviation 0.1, and of course we'll need 1,000 samples. So let's go ahead and do that. Okay, so now that we got x and y, we can go ahead and plot it just to make sure it's doing what we think it should. So let's plot x to y using Seaborn. And GitHub Copilot almost gives me what I want. I mean, this would actually work, but let's just put x equals there, y equals there, so it doesn't give us any error message. And we'll put this one so it doesn't spit out any extra text. And let's also plot the line. Let me do that one in a comment. Plot the line y equals 3 plus 2x. And it goes ahead and does that one, but that's not going to work because it used matplotlib. So this will give an error, and I didn't import matplotlib. So let's just do it with SNS, and hopefully it'll spit out the correct code. There we go. Great, so we have a bunch of points that are close to this line, but not exactly on it because we added some random noise to y. Next, we're going to go ahead and solve for the least squares solution. So given just the blue points, we're not exactly sure what the red line should look like, and we're going to try to solve that. So let's go ahead and do that. The first is a pre-processing step where we add a column of 1s to x. So let's do that. Add a column of 1s to x. And it does it like I want it to, but I'm going to rename this variable since I don't want to be renaming variables in different cells. And let's just print x.shape to make sure it did what we want, and it should be 1,000 by 2. Perfect. And let's just have a quick look at x. And again, we see 1s in the first column, and that'll be for the intercept. So I'm going to go ahead and delete this. We don't need that anymore. And now we're ready to move on. Next, let's solve for the least squares solution. And we're going to call the variable beta. And we're going to use NumPy, so np.linalg. And then from linalg, we're going to use the method solve, which will solve a linear equation. And it turns out that the least squares solution is the solution to a linear equation, which is exactly given by this. And let's print beta, and it should be something close to 3, 2. And wow, it's very close, almost exact. Okay, so now that we have the least squares solution, a natural question is, how good of a guess is this? Well, there are several different ways to go about asking this question. We're going to approach it from the perspective of p-values. It turns out, and as we saw in the previous video, that the betas are normally distributed. But what does that even mean? If we go back here to when we defined y, we added some random noise. So if you run this experiment many times, changing what the random noise might exactly be, you'll get different betas for your solution. And it turns out, if you look at all these different betas, they have a particular distribution, which is a multivariate normal. But how do we actually figure out how likely this beta is a good choice for the original problem of finding the least squares solution? To apply this test, we're going to need to know a mean and a standard deviation. For the mean, we're just going to use the values we computed for beta, but for the variance, we're going to use something else. Okay, so in the previous video, we talked more about this covariance matrix. So it turns out, as we discussed in the previous video, that beta has a normal distribution, and this is actually the covariance matrix. This capital X is something we saw above. This was just the 1000 by 2 dimensional matrix, which consisted of all our data points. Sigma squared is actually something we saw above, but let's go back and check it out. So when we defined y, this 0.1 is actually sigma. In practice, we're going to have no idea what sigma is, and we'll have to infer it from the data. It turns out that a good approximation from sigma can be gleaned from our actual model, which we'll discuss below. But in conclusion, sigma is given by this 0.1, but to actually compute it in practice, we're going to have to use another way of computing it because we won't know exactly what this should be. The reason we won't know is because data is not usually created synthetically, and random noise is not something that we introduce, but rather have to observe. So we're back here, and we have to figure out how to compute this sigma. It turns out the way we can compute this is by actually using our linear regression model to predict what the value of y should be and compare that to the actual value of y. So let's go ahead and do that. So the first thing we're going to do is compute our predictions. And it turns out we can actually do these computations in parallel, and we have this. So this will actually give, let's just check. So print predictions.shape, it should be 1,000 predictions, one for each data point. Now, to approximate sigma, all we need to really do is actually compare these predictions. The next thing we have to do is compare our predictions to our actual y value. So let's go ahead and do that one. So there we are. And if we run this, of course, it shouldn't be 0 like GitHub Copilot suggested, but it's just a big vector with all the so-called residuals. So let's actually define this variable as residuals. And let's just check the residuals shape just to make sure it's 1,000. And it is, so that's perfect. So our sample sigma, or we can actually do sample variance, which is sigma squared, and it'll actually be np.sum. So we're going to sum the residual squared. And this will give us an unnormalized version, but in fact, let's actually do this just to see. And this will be a bit large number, largest, it'll be about 10, which is not exactly close to 0.1 squared. And the reason why is because we need to put a mean here, not a sum. So we get the average. Let's go ahead and do this, and we get it. So this is what we're going to use for our approximation of sample variance. We're not going to worry about any bezel correction or anything, so if you know about that one, we're just going to skip that. I also want to mention that the sample variance is not quite the 0.1 that we saw above, and that's because we would need to take a square root to get the standard deviation. So let's go ahead and do that and just see what we get. And yes, it's close to 0.1, so our sample variance is quite close to what we used to generate the data. Going back to this above formula, we now have everything we need to compute it. So let's do sigma equals the sample variance, which is sigma squared. And actually, GitHub Copilot suggested exactly what is the correct thing. And let's actually print out sigma. And we have a 2 by 2 matrix, and here we are. Now let's go ahead and compute p-values for beta 0. So beta 0, remember, is our approximation to the intercept. So again, it's something close to 3. So the first thing we do is start by getting sigma 0. And this will just be the top left entry of sigma. This corresponds to the variance of beta. And we're going to take the square root of that. So that's why I took the square root. And let's just print sigma 0. And it's something pretty small. Now, in order to do this, we're going to actually have to use the student t distribution. So let's actually go ahead and do that. So in order to do this, we're going to apply the student t-test. So let's go ahead and do that one. It turns out that there will be easier ways to do what I'm going to do, but I'm just going to use NumPy for it. So let's do samples t equals np.random, not normal, but standard t. There we are. So we're going to have actually 999 degrees of freedom, and that corresponds to the size of the data minus 1. And the size will make it, we're going to make it much bigger than 1,000, so because this is just going to be used to approximate something. And let's actually plot the samples seaborn, not SBS, SNS. And let's do a hist plot, not that one. And let's do data equals. You can see that it looks kind of normal, but it's a student t distribution and not a normal distribution. So let's actually get the 0.975 quantile so that we can actually get the p-value. So let's do that one, quantile. There we go. And let's print it. And there we go. So we get a number 1.95. What this number means is that roughly 97.5% of the data is less than 1.95 in this distribution. So let's go ahead and compute the confidence interval. Confidence interval. That's something we already had. And there we go. And let's actually print these. So this is the 95% confidence interval. Note that we take our t-value and multiply it by our sigma 0, which we computed above, which is an approximation for the variance of beta 0. Note that this is a pretty small interval. This means we have high confidence that beta 0 lies in this interval and is somewhat close to 3. Of course, 3 was originally what we inputted into the model, so that's good to see. Now let's go ahead and do the same computation, but just use a Python built-in package. So let's use Statsmodels, and let's use linear regression. For linear regression, see what it gives us. We won't need that one. We already added the constant here, so that's fine. And let's go ahead and do that one. And look at the p-value. So for the constant, it's 2.995 and 3.02. And this one is 2.995 and 3.02. So it matches up perfectly, which is nice to see. And in fact, that's how the p-value is computed. We use our approximation for the variance given by this formula up here, and we use the student t-test to finish our computation of the confidence interval. So in conclusion, we saw how Statsmodels computes the p-values, and now you can do it on your own. I hope this helped you understand a bit better what's going on under the hood. I think that's enough for today, so thanks for watching and have a great day.